Good afternoon. I'm Neil Coles, and I'm the empowerment lead for Microsoft's AI Safety and Security Group. You might be wondering, what does an empowerment team do? Well, we provide answers to the question, how do we make safer and more secure AI systems? We do that through a combination of methodology, business processes, and education or training. Today, I'm going to discuss why adding AI to a system makes us all safety engineers. And by the way, when I say safety, I'm using safety in the broad sense of harm, everything from physical injury through emotional and psychological harm to AI-controlled ransomware and societal destabilization through disinformation and propaganda. But before we dive in, a quick content warning. Some of the examples I'll be using cover sensitive topics, including domestic violence, extremism, suicide and self-harm, and gender stereotyping. I don't go into any detail on these topics, but I will be touching on them at a high level. With that in mind, let's get going. So since its inception, the focus of our field has been on rapid innovation. We've tried out and invented new technologies for everything from computing, communications, personal computing, to gaming, industrial control, and office automation. We tried out these ideas on one another, developing tools for ourselves and building a thriving open source community. And importantly, we could move fast and break things because the consequences of something going wrong were ultimately limited. So we've tried to split up our profession. We had a few serious bits like medicine, critical infrastructure, like power plants, and aerospace, where we had to have very serious testing and attention to detail, and people wore ties and had Gantt charts. And then we had the exciting stuff, the things that happened in places like Silicon Valley, where everyone was free to innovate as fast as they could, just crank out the best ideas you have and keep iterating on them until they work. And we've succeeded. Today, the technologies we build are fundamental to nearly every aspect of human life. They're where people make friends, find jobs, and build communities. And they're also where people find other kinds of communities, lose jobs to automation, get bullied, harassed, and stalked, and live or die by the system. What we do matters. Today, if your software matters at all, it matters to a lot of real people. When we build systems right, people thrive, and when we build them wrong, people suffer. The consequences of our mistakes are measured in millions of dollars if we're lucky, and in lives ruined or lost or democracies overthrown if we aren't. We have succeeded. Computing is now fundamentally woven into all aspects of our lives and societies, and that means what we do as a profession matters. As the saying goes, with great power comes great responsibility. So, what do we do about it? All of engineering has two sides. Firstly, there's product engineering, how the system should work. And then there's safety engineering, how the system should fail. Most engineering disciplines barely distinguish between the two. Civil engineers are basically safety engineers who sometimes build bridges. In computing, we've historically separated these two sides and trained our young engineers almost entirely on product engineering and relegated safety, including security, privacy, reliability, and abuse, to things we think about afterwards. And if you've ever tried to retrofit security or reliability into an existing system, you'll know why this doesn't work. So why am I talking about this now? What makes AI different that means we need to put safety back at the heart of what we build? It boils down to two fundamental properties of AI. First, they're probabilistic systems. So for some percentage of the time, by design, they will provide the wrong output. And second, they are non-deterministic. The same input will not produce the same output a second time round. As a field, we're not used to including non-deterministic, probabilistic components into the systems we build. Think about that first property for a second. It means that the system can now expect failure as a normal part of operation. Failure handling is not usually at the forefront of our minds when we build systems. How many times have you seen a system whose failure mode is throw an exception and hope it's caught somewhere up the stack? That doesn't suffice for AI, where failure is a normal condition. You'll also hear lots of numbers bandied around. This AI model is accurate 95% of the time. Well, if that system is used by 1 million people a day, then it will fail for about 50,000 people a day. That's roughly 1 every 2 seconds on average. Safety must become as fundamental to our work as breathing. I'm not going to try and cram an entire course on safety engineering into the few minutes I have here. We're working on some approaches, and hopefully we'll be able to share those with you soon. But I do want to talk about some basic principles and walk through a couple of specific cases to show you what went wrong and the lessons we can learn from that. So first, let me just outline the basic principles of safety engineering. All of the frameworks you'll ever see boil down to this. First, know the way the system might fail as intimately as the way the system should work. Brainstorm those failure scenarios and keep that list as fresh as the normal user scenarios. And for each failure scenario, have a plan. Now, that plan might be eliminate the failure, reduce how often it could occur or the severity of the failure, give the system's users a way to solve it themselves, or have a response plan for when things go wrong. And this quote from Andreas Schur is a good reminder. Never forget that there are people behind the numbers, and the scale of the systems we build means that failures can affect a lot of people. So how do you do that brainstorming to find the failure scenarios? There's a couple of related approaches that I recommend, and I'm going to walk through briefly. So in the first approach, look at the system through 3 lenses. To begin with, the system first lens. What are the components, including the users and the operators in the system? What happens if a component fails or gets bad input? Next lens is the actor first lens. What might happen to someone who wants to use this system to achieve a harm? How might they use that system to attain that goal? And the final lens is the target first lens. Who might be affected by this system? And don't just consider those who are directly affected, but also those who might be indirectly affected by the system. What can be done to make them more or less vulnerable to the impact of the system? How could they respond if they're impacted by the system negatively? And this point might be last on the slide, but it is a very important one. For this brainstorming to be effective, you must have a broadly diverse team. You need the knowledge of lived experiences that are different from yours. So the second approach to brainstorming looks at it from a slightly different perspective. First, we need to understand the scenario that we're trying to solve. And I'm not talking just about the technical scenarios for a system, but the broader context and problem that the technical system is a part of. As we'll see later on, if we limit ourselves just to looking at the technical components of the system, we'll miss both safety risks and possible opportunities for mitigating those risks. In the broader scenario, the aim is to get an understanding of the actors or players involved, both those who directly interact with the technical system, as well as those who are involved in the broader scenario, but may only indirectly interact with the technical system. The best way to do this is to talk to the users, the experts, and representatives of those who deal with the scenario day in, day out. If you have that opportunity, take it. And this is a place where user research can be a great help. If that's not possible, then look for the write-ups, the research studies, and the descriptions of the scenarios written by those experts. And at a minimum, conduct some basic research yourself. You can do that on the internet with the usual caveats, but it can usually provide a broad context understanding of the issue. And with all of these, bear in mind that, as I said earlier, you'll want to try and get the diversity of perspective to get the broadest possible understanding and widest range of actors possible. So once you've got that list of actors for the scenario, you want to ask yourself 2 questions for each actor. First, if the actor was trying to cause harm to another actor in the scenario, how could they take advantage of the scenario to achieve that? This is looking for the ways that actors can weaponize the scenario. And it doesn't necessarily have to involve the technical portion of the system at all. For example, in the US, the cost of legal defense has often been used by wealthy groups or individuals to try and stifle free speech. That's a weaponization of the legal system to censor unpopular opinions. Secondly, turn that first question on its head. How could the system cause harm or have a detrimental outcome for the actor? And the final step is to look at the AI component of the scenario. As I said earlier, AI models are probabilistic, so they will fail some portion of the time. Assume that the AI has failed. How does that play out for the larger scenario? For AI classifiers, consider both the false positives and the false negatives. For LLMs that are performing summarization, think about what would happen if a key point was left out of that summary, or a key point was fabricated by the LLM. Also look to see if the AI system is being intended to replace or augment human judgment scenario. If it is, that will often point you in the direction of ways the system can fail that may be unanticipated. And finally, if the scenario is about improving humans' efficiency by reducing a bottleneck, think very carefully how the AI results will be assessed and reviewed by humans. And a favorite example of mine here is the radiologist scenario. Radiologists are super busy and it's hard for them to get the results back to the doctors and patients in a timely fashion. So what if we had an AI do the routine examinations of the images? Sounds great, takes the burden off the radiologist, and the patients and doctors get their results sooner. But the AI is going to get the results wrong some of the time. Well, we've said then we'll mitigate that by putting a human in the loop to review the results. Who's the right person to do that review? The radiologist. Wait a second, we've just said that the AI is going to take some of the workload off the radiologist, but now we've added the radiologist back in, and we're saying the radiologist is going to review those AI results. There's a tension here, and mitigating this tension requires very careful thinking right across the scenario, and in particular requires engaging UX design very early on. At the end of these three steps I've just outlined, you should have a list of actors, the ways that they can use the scenarios for harm, and the ways that they can be harmed by the scenario, as well as a set of ways that AI failures can harm actors in the scenario. Collectively, these form your safety scenarios. So now I'm going to switch gears a little and review a few examples of safety failures and see what lessons we learned from them. First is Therac 25. This was a computer-controlled radiation therapy system that was launched in 1982. And it has three modes: a setup mode to position the patient. In this mode, the therapy beams are off. There's an electron beam mode that targets the patient with a low current electron beam, and an X-ray therapy mode that targets the patient with high energy X-rays. And earlier versions of the system used an electromechanical interlock to switch between those three modes. Therac 25 was the first one to use a software system. Well, what could go wrong? First, there was a race condition when changing between therapy modes. If you selected X-ray mode, but switched to electron mode within 8 seconds, then the beam stayed in the high energy X-ray mode. Secondly, in setup mode, the low energy beam would just fire at random. Wasn't supposed to be possible, but it was happening because of a bug in the system. And the consequences of these two bugs were very real. 3 people lost their lives and 3 were severely injured. So what were the mistakes? The investigation that ensued didn't find a single flaw, but rather a systemic pattern of poor design. Unlike the old mechanical interlock that physically prevented never-happen configurations, like the electron beam turning on in setup mode, the software didn't contain safety checks looking for those never-happen configurations. The system didn't give the users enough feedback on the actual state of the system compared to what they expected the state to be. And finally, all errors were just reported as malfunction with some numeric code after it. And they didn't make any distinguish between safety critical errors from other less severe issues that also cropped up. That led operators to hitting the proceed button because normally that was the right thing for them to do. So what lessons can we draw from this? In complex systems, and almost all software systems that we build are complex systems, define the safety invariants and check for them. The operator flow must be included as part of the safety design and evaluation. And don't think that user experience is just about what this software system shows on a screen to an operator. It's also the broader system and the process that the software is part of, the larger socio-technical system that comprises the entire system that you're working on. Now, to a very different example, Google+. Google+ is Google's social network that was launched back in 2011. It had a very privacy-centric design with circles of friends as a key construct. When it was launched, only 3 fields in a profile had to be public: name, picture, gender. Why did gender need to be public, you might be asking? Well, in most languages, to say X shared a picture with you, you need to know the gender of X and your gender to be able to construct the sentence. Those 3 fields don't provide a lot of information. There couldn't have been a problem here, could there? Well, unfortunately, yes. As soon as the service was launched, people were scraping the service to find women and sharing links to their pictures. And this is just one example of various groups hostile to women that sprang up in the network. And for a social network, the initial population sets its culture, and that culture then shapes the future population that will join. And the initial culture here drove women away, which is not what you want when you're launching a new social platform. So the lesson here is very basic, but unfortunately, it still needs saying all too often. Without diverse opinions in the room that are listened to, you will miss safety and threat scenarios. And the final example I'm going to walk through is ViaGen. Now, ViaGen is a system that's used in Spain, which was the subject of an article in the New York Times a few weeks ago. And just to flag the content warning again here, this example and the next 5 slides involves a discussion of domestic violence and its consequences. So domestic violence harms and kills thousands every year, and the police resources that are allocated to it are limited. So the idea that they had in Spain was to use data to create a model that would allow them to optimize the allocation of those scarce police resources. The model was fed the answers to 35 yes/no questions that the police would ask when responding to a domestic violence incident, and the model would return one of a 5-level risk classification that they would then use to shape the police follow-up response. And as they recognized that the system might misclassify that risk, part of the rollout included educating police and judges who use and interact with the system to use their better judgment and override it when they needed. If you're saying or thinking, oh no, right now, then you've been paying attention. What happened? Well, according to the New York Times article, 95% of the system predictions were accepted. That's a clear sign that the safety mechanism of educating the police to override it isn't working. Since the system was introduced, 247 women have died. And a judicial review of 98 of those deaths has revealed that 56% of those women, that's more than half, were rated negligible or low risk by the system. Now, for those women who received negligible or low risk ratings, not only was police assistance no longer available, but they also found that the risk rating that had been assigned was being used as evidence against requests they were making for restraining orders or other protective measures. And Overall, it might be helping to reduce deaths and serious violence. It's too early to tell, and we mustn't forget that we're just looking at what was reported in the news article. But at least from the data that was in that article, it looks as though if you're rated at the low end of the scale, you are potentially in trouble, and very high consequence trouble at that. So, what was missed? One of the oldest principles in computing, garbage in, garbage out. The world's best model doesn't help you if you get bad inputs. And here, people being abused often depend on and or fear their abuser, or they're ashamed that they've been abused. And you're asking them to give honest answers to intimate questions to a usually male stranger who was selected at least in part for machismo, who may well have ties to your abuser, especially if you're living in a small town. Did they really think they were going to get good data here? The people here most in danger are the people most likely to lie. Now, the system's goal is to reduce the load on the police and better allocate the scarce resources. But the police are being told to override the system if you have better judgment. Yet to do that, they have to justify that judgment, which is more work for them. There's a mismatch in incentives here, and that's part of the reason for that 95 acceptance rate of the system's risk ratings. And when we were discussing this scenario internally, we came up with some other risks as well. Lack of resiliency to insider threats or bias, assumptions in the system, for example, always a male abuser of a female victim, the police officer is a trusted neutral helper. And some of these examples of risk came up because of the lived experiences of the people on the team who were discussing it. And this, again, is an example of why having a diverse team matters so much. And finally, the base assumption here that more accurate routing of police resources is the appropriate problem to solve doesn't appear to have been questioned. So what lessons can we take away from this? And as a reminder, these lessons are just from reviewing the news article. We don't know the safety approach that the team who actually built and deployed the system took. So it looks like there were lots of good researchers building the system, but few folks with actual operational experience on the ground. Don't do that. Make sure you have lots of people with operational experience in the problem space you're building the systems for. Start with the what could go wrong modeling. Don't wait until failures are happening in the real world. Do it at the same time you're constructing your user scenarios, and look at it again when you're deploying the system. If they'd done that, the system probably would have been designed in a very different way. And it's not enough to test your model. Most failures happen at the integration level, so make sure you plan and do sufficient testing once the system has been integrated. And again, don't forget that there are people behind the numbers. Even if your system is 95% accurate, and that's a hard claim to make, what happens to the 5% that it is wrong for? How severe are the consequences for them? In this system, people died because the system failed them. And now that won't be the case for the most of the systems we build, but you must be able to answer the question, if the system fails for someone, what consequences will it have for them? And you need to be comfortable with that answer, both for the most vulnerable participants and the most serious consequences before you release that system. So, what are the key takeaways I'm leading up to here? What we build matters. It doesn't have to be medical or an aerospace system to have serious consequences when it goes wrong or is used in the wrong way. Even seemingly innocuous things such as image creators can be used to shame, bully, or harass people. Safety is thinking about those failure cases up front and having a plan to address them. Safety includes everything. From a safety view, nothing is out of scope. Just because someone used the system in a way we didn't expect or don't support doesn't mean we get to say, oh, that's not our problem. If it's your system and someone or something can be harmed because of it, you need to have a plan. We as a discipline need to embody safety. We need to be looking for and modeling safety threats from the moment we imagine the system. And we must know those safety issues as well as we know our own features. Thank you very much for your time. Now go build safer systems.